Welcome everyone, welcome. We're just letting people in, so just give it a few minutes while the waiting room gets emptied. Just like in real life, there's going to be a time between moving into a room and out of a room. It's just a little bit faster. It's just a little bit faster. Just imagine you were just waiting in a hall in like real life, and you're now walking into a room and we're just standing at the front of a room. Same thing.
The difference is I don't have a Danish.
Yeah, the difference is there's not three-hour-old coffee, hopefully, and stale Danishes sitting around.
I wish they had guava pastries. That'd be like exotic if they could do that. I love guava pastries.
I don't even know what that is. It sounds delicious.
It's like a cherry pastry, but less. The sweetness is a little bit less sharp, so you can eat it more.
I have to order it on DoorDash. Maybe it'll show up by the end of the session.
Yeah, everyone, we're not plugging DoorDash, but whatever your delivery method is of choice, feel free to put in those orders now and get those pastries delivered. We'll just wait another few minutes for the waiting room to empty. And yeah, as Louise said in the chat, if you have questions throughout the workshop, please feel free to post them. That's pretty good. That's almost everyone. Oh yeah, Rob getting pizza. That's awesome. Oh, and Will is asking Kwabena if you're from Ghana. I guess based on, we were just chatting.
The name is from Ghana. I am not from Ghana though.
I think with that,
Dad went on a spiritual journey and everyone got a new name before I was born.
That's what spiritual journeys are for.
Yes.
Cool. With that, I will go ahead and do some quick housekeeping before we get started.
How many
waiting
people?
Room is emptying.
Oh, everyone's out, or?
There's a few more.
Okay.
There's 3 left in the waiting room. With that, let's see. Welcome everyone. Welcome. If you're experiencing any audio issues with your device, you can use a phone call in this workshop. The numbers were just posted in the chat. Feel free to call in case you're having audio issues. Today's presentation is being recorded and will be available within 24 hours on the ARM DevSummit site. We welcome your comments and questions for the speakers. Kwabena is probably going to take them as we're going because this is a hands-on workshop. This is also the last workshop of the DevSummit, so saving the best for last, and welcome everyone. If you have any questions about our code of conduct, please read the facts on the ARM DevSummit site. If for some reason Zoom meeting ends prematurely, please try the link again from the ARM DevSummit and just wait a little bit longer. With that, I think we can go ahead and get started. I'd really like, it's the honor and privilege to introduce Kwabena Agyeman, OpenMV, one of the founders for OpenMV, and he'll be conducting this workshop. Hopefully everyone, you have your hardware that was sent to you ready, and take it away, Kwabena.
Hi, everybody. Let's go back. Yeah, so welcome to Zoom Apocalypse, session number 10 billion. So today we're going to be talking about simplified deep learning using an OpenMV Cam, Edge Impulse, and an Arduino. In particular, this is going to be a cool workshop where we explore how to use Edge Impulse to train a neural network very, very trivially to detect random objects. And in particular, what's amazing about this is that we're going to show you how in literally 30 minutes or less, how you can train a neural network to detect random things without you having to know any complex Python code or etc. All right, so first, a little bit of background on the OpenMV Cam. So this is a project that me and my co-founder Ibrahim started back in 2013. The goal was basically, let's see if we can strap a camera onto a microcontroller and see how fast that we can make code run and see if it's possible to do computer vision of a microcontroller. At the particular point in time at which we started this project, the concept that you would have a machine vision library for a microcontroller was very much just one Stack Overflow article saying that it was impossible. And since then, we have really expanded the concept that, yes, this is possible for people to do, and that it's actually not that slow and is capable of doing real work. And so the OpenMV Cam is our hardware exploration platform for this project. It is a ARM Cortex M7 microcontroller. So we basically find the fastest ARM microcontroller on the market, or the fastest microcontroller in general. We have an open source software and hardware system that the product is based on. And the product is programmable in C, powered by MicroPython. Sorry, it's programmable in Python, powered by MicroPython. The firmware is written in C, and so all the computer vision functions are actually optimized C code. And then MicroPython is running on top of it to coordinate all of the interactions and make it so that it's not super hard to write firmware and write code to make this thing go. In particular, by what I meant by us using fast microcontrollers is that we're using a 480 megahertz ARM Cortex M7 for our current product. This is equivalent to basically a Raspberry Pi 2's ARM CPU, or effectively equivalent to a 1 gigahertz ARM 9 in terms of its core mark score. It does not have ARM Neon though, so it of course isn't as fast as application processor, but from a single threaded perspective though, it's about as performant as an old application processor. Additionally, we have 1 megabyte of RAM on board and 2 megabytes of flash. Now, this is our original OpenMV Cam H7 picture here. We have newer ones coming out that have SD-RAM attached with quad SPI flash to increase what we can do and increase the ability of the project. And today you're going to be working with the OpenMV Cam H7 Plus. Anyway, so just a little bit of background on the OpenMV Cam project. This exists because of the CMU Cam project back in the day. I went to Carnegie Mellon University, and the Carnegie Mellon University camera was created back in 2002 as basically the first machine vision camera for a microcontroller. It was based on a SX processor and did line processing on images. Basically, it read in a frame, and it did color tracking on for one object in that frame. And the first one was pretty popular back in the day, back in 2002, when no one else was doing this. There was a CMU Cam 2 created afterwards, which was popular for first robotics, and then a CMU Cam 3 where they added Lua scripting and an SD card and the ability to do face detection. Our OpenMV Cam kind of, is conceptually the next generation of that. Finally, I did the CMU Cam 4 based on a propeller chip that was a little bit lower cost than the CMU Cam 3 and able to track color blocks. And finally, the current model of the CMU Cam is the Pixie, which can track multiple color blobs at the same time. The CMU Cam line of processors, though, sensors, lack something, which is the ability to be programmed to do different things than just what its firmware comes with. A lot of these different previous machine vision products all pretty much needed a host processor in order to connect to, in order to do anything useful. They were not a platform by themselves. And so the OpenMV Cam changes that whole idea into making the sense, plan, and action all on one processor so that you can just use an OpenMV Cam to do everything. All right, and then finally we have got a question here. So we don't use the CMS DSP software for image processing. It's actually not that performant. I will say our original code base was written pretty much as generic C code and not heavily optimized. This year, we started a new optimization project where we hired a performance optimizer who knows how to write fast code. And we've been getting 4x speed boost on most of our algorithms that he's touched. I'm currently right now working on a alpha blending / bicubic and bilinear scaling pipeline with area scaling also. That will pretty much improve our ability to do rendering up to the same level as OpenCV. And for this pipeline, I'm heavily utilizing all of the SIMD instructions on the Cortex M7 and Cortex M4 processors. Before, I was never utilizing these because I honestly was confused on how to use them correctly. They're very limited, but they actually make short work of doing bilinear and bicubic scaling. They make that incredibly fast. And so we're going to have some great code coming out later in the year for that.
Just to interrupt a moment, we've got a question in from Ram asking, does the camera image processing software on the Cortex M7 use Sempsys DSP for image digital signal processing?
Yes, Rob, I just answered that. Can you guys hear me?
Yep.
Yep, my mistake.
Oh, okay. All right, sorry, I should have paused for a sec. Okay, finally, you program the OpenMV Cam using OpenMV IDE. Basically, we realized that the tool that you use to develop the system is very important. And so OpenMV IDE integrates all of the nice tools and features that you need to play with OpenMV Cam. This lets us quickly add new features that we want for our customers and make the tool as useful as possible. Also, we wanted to just raise the bar on microcontroller programming environments. So we integrated a nice C++ based editor based on Qt Creator. Has a frame buffer viewer built in, histogram viewer, very nice serial terminal with basically infinite scrollback, and a very, very nice text editor. All right. So finally, what do people do with OpenMV Cam? So primarily right now at our roots, we were a hobbyist platform for people to track colored objects. As the project has grown over the years, we started to see the OpenMV Cam appearing in professional applications for equipment, for people trying to build systems that are measuring process control. And we're also seeing the OpenMV Cam now being picked up for environmental monitoring. And then recently, announced on Tuesday, we have a partnership with Arduino, where we're going to be supporting machine vision software for the Arduino Portenta. And so with this, we're really going to be trying to push the limit on what we can do with adding all the connectivity features, such that you can have the OpenMV Cam deployed in a low power environment and able to sense, plan, and act on board and relay that data back to the IoT web cloud. Cool. Any questions before we get started with the image classification workshop? All right, cool. Okay, so let's get started with this. So, don't need this anymore. So, everybody, do you have your OpenMV Cam connected to the computer? So for this workshop, you're going to need the OpenMV Cam H7. What you're going to want to do is to connect your OpenMV Cam H7 to your computer. You should have updated the firmware, and your firmware needs to be at firmware version 3.67 or 3.68. We just released 3.68. This includes CMIS NN support for the neural networks. And so it is 4x faster at running a neural network than 3.67. So if you have that, that'll be great. We also released a new version of the IDE, version 2.64, and then we released another yesterday, 2.65. If you have either 2.64 or 6.5, you should be good to go. On 2.65, we just fixed some issues for connecting with the Arduino Portenta. So as long as you have 2.64, you should be good. Once you connect your OpenMV Cam to the computer, you should see this little option right down here. Can you see my cursor? There's a little connect button. So if you go ahead and click that, you should connect to the camera. At that point, then you should be able to press, you should see this untitled hello world, or an examples basics hello world.py. And you should be able to run that. And when you do, you should see an image of what the camera sees. And so for this workshop, we're going to be training a neural network in particular. And what we're going to want to do is to make sure that our camera is pointed at a flat surface that's relatively solid and static. And by the way, if it hasn't been shared already, this is where you can find the resources for this whole workshop. I have videos that are already pre-recorded of this. Oh, yes. Okay, well, we just recompiled it for Catalina. Did you have a version that worked before, Richard? Okay, Rob Morey has a solution for you. Ah, that's weird. Okay. Yeah, we do digitally sign our IDE, so maybe it's just because it was brand new, Apple hasn't had enough downloads of it yet to verify that it's not a virus, I'm guessing. It is signed with Apple Developer ID key. Okay. Yeah. Anyway, so for everyone else, where this is working, I just posted a link to Google Drive on the chat, and so you can find video clips of me recording how to do this, along with the script on what you need to do, along with the PowerPoint and files for this whole workshop. So if you fall behind, you can just go look on that Google Drive link, and that'll give you all the resources you need to work with so that you can complete the workshop at any time. Cool. Okay, I'm just going to wait a few seconds. So for setting up the OpenMV Cam, what you need to do is point the camera at some kind of flat surface, either a wall or point it downwards at a desk. For this example, what we're going to be doing is training a neural network, as I said before, to classify objects. And so for this, pretty much, we're going to be working with, sorry, I'm looking at the chat. We're going to be classifying objects. And so we want to have a static background that's more or less boring for the camera to look at. It's okay if you have some kind of, if you can't get a fully static and flat background, as long as whatever is in the background doesn't change between images. We want the neural network basically to learn just the thing that we're holding in front of the camera and nothing else. So to begin with this, what we're going to do, after we have Hello World working and we can see the camera streaming and we have our firmware updated to the right version, we're going to switch over to using something called the dataset editor. So we're going to stop running the script and we're going to go to Tools, Dataset Editor, New Dataset. And this is going to open up OpenMV IDE to create a new dataset. So you need to give that a folder to put that dataset in. And so we're going to call this workshop. Okay. And we're going to click select folder. And so what OpenMV IDE now is going to do is it's going to use that folder that we just created a new data set in, and it's going to store images in that folder of what we're capturing to train a neural network. And it also opens up this thing called the dataset editor script. And so this script is pretty simple. It's just going to capture a frame from the computer and display that on what the OpenMV Cam is seeing. The idea, though, is that if you were trying to train a neural network and you wanted the ability to, if you wanted to apply lens correction first, or rotation correction, or some kind of median mode or midpoint filter, you would do that in this dataset editor capture script and make sure that you've applied those same filters to the data set that you're going to apply in real life, so that the images you're capturing looks the same as the images that you're actually running the neural network on. For this example, we're not going to apply any filters. We're just going to use raw images. And so we're not going to edit the script at all. After that, we need to start creating class folders. And so class folders are the way you organize images for a particular class that the neural network will recognize. So for our first class folder, we're going to call that a screwdriver. And for this demonstration, you really just need to have 3 random objects that look different, really, for this. The whole point of this demonstration is that we want to show off how powerful TensorFlow is. We're not going to grab any type of object that looks in particular. You create the class folder after you open the dataset editor by going to the left bar of the IDE, and there's a new class folder button that should have appeared for Jeff Bradham. All right. So once you create that class folder, again, this can be any random object you have lying around. The whole point again is we're trying to show off that you can train a neural network to literally recognize anything. So once you've created that new class, you're going to select the class folder, and then you're going to grab that object and put it in the OpenMV Cam's field of view. So I put a screwdriver in the field of view. And again, pick whatever object you want. We're just going to use 3 different objects. Okay, once you do that, the RAM, the new dataset editor class should be underneath. You have to open the dataset editor first. So you have to go to Tools, Dataset Editor, New Dataset, and then create an empty folder and select that, and then click OK. All right. Yes, okay. Once you do that, then you can select the screwdriver class folder, and you can click this button over here called Capture Data. And that's going to take a picture of that screwdriver, okay? And so we want to get pictures of the screwdriver without our hands in it. So if you take a picture of your hand in it, you want to delete that. The whole purpose is we're now building a data set of images. And so we just want to rotate the screwdriver around and kind of give it some random translation and rotation offsets. Andre, it sounds like you're in the very first part of this. Check if there's a little USB option next to your IDE, OpenMV IDE, if you see a little USB connection option. If you don't see that when a camera is plugged into your computer, that means your computer has not even enumerated to OpenMV Cam being attached. Check that your USB cable then is a USB data cable and power. All right. And so we're just going to take pictures of this object in different rotations. And it's pretty boring, but this is the idea of building a data set. Our goal is to get a whole bunch of pictures of the screwdriver in the field of view, somewhat occluded. And we're going to use data set augmentation later to blow up this smaller data set into a much larger one. We want to capture about 30 images of this object just sitting around in the field of view to give the neural network enough information to kind of generalize what a screwdriver looks like.
Can you hear me?
Yes, I hear somebody.
Yes, I Elton here. Yeah, I've got a quick question. Does it need to be the same screwdriver all the time, preferably, or can you exchange them for others?
You can use 2 different screwdrivers if you feel like it. That'll make the neural network have to work harder to learn it, but it should be fine.
Cool, thank you.
Obviously, don't make the objects look too entirely different, or the neural network is going to have a very hard time then recognizing them. Like, for example, if you use 2 PCB boards, that is going to definitely make the network, like the network, for example, I'll show you later in the next data set. Yeah, anyway, so we want to get about 30 images of this screwdriver, okay? And so I've got 27, 28, 29, and 30. Cool. Okay, so that's our first class, screwdriver class. We've got a whole bunch of images of that. And so before we move on, quickly go through your data set and make sure that you don't have any random objects in there, okay? And so I'm looking through my data set and it's just the screwdriver. My hand is not in the picture. You wanna make sure your hand doesn't get in the picture because that's gonna screw up your data set. All right, next, when you have next we're gonna create a new object. And so we're gonna call this Portenta. And I'm gonna put my Arduino Portenta in the field of view. All right. So we're going to take pictures of that guy now. And what I meant by circuit boards is that the neural network is going to recognize that this is a circuit board looking item. And so if you put another circuit board around you, like in your, if you put another circuit board in the field of view after we've trained the network, it's highly likely that the neural network will classify any circuit boards it sees as a portenta because they kind of look like a circuit board, which a portenta is. So that's why I said it's okay to use 2 screwdrivers because it's most likely going to classify those two objects as screwdrivers. But be careful on giving it multiple images of different, very similar looking objects and expecting it to differentiate between them, unless you build a larger data set. And so just for a note, like for a real application, you would do something very similar. So I can say, for example, that I've gotten customer requests where folks want to use use TensorFlow, for example, to see what, imagine if you have bowling balls rolling down a ball return chute, and someone wants to know, how do I identify the bowling balls flying by? So that's a great example of how TensorFlow can, be helpful for that application. You can basically train your neural network on different pictures of a bowling ball moving down the chute. And you similarly have to do the same process of collecting a data set of pictures of different bowling balls in different orientations, flying down the chute, and then putting those all into labeled folders in order to train a neural network to classify those objects. So with neural networks, basically, the work, instead of being on the algorithm side, really is on the data collection side. Cool. So now we have about 30 images of the portenta. And so we should be good to go with that. All right. And finally, we're going to create one more class folder, and we're going to call this the OpenMV Cam. Okay. And we're just going to take some pictures of an OpenMV Cam now. And yes, this is painfully slow and boring to do, but that's what it is to train a neural network on a data set. What's awesome though is that the power of this, like if you think about how would you differentiate these objects, normally using traditional computer vision methods, like how do you tell between a screwdriver, a portenta, and the OpenMV Cam? It's not easy. Yes, you could use color tracking, for example, to split these object classes, but that's not generic at all. Like, depending on the new random object someone asks you for, it's almost an impossible task. I've gotten customer requests where someone asked me, hey, Kwabena, can we use the OpenMV Cam to differentiate between wood grain? So they want to know a bit the difference between wood grain going horizontally this way and wood grain going the other direction. And any type of generic computer vision algorithm would be impossible, could not solve that problem. But if a TensorFlow neural network, it's a trivial thing to ask for now. So that's what the power of being able to run TensorFlow models in the OpenMV Cam kind of unlocks. Pretty much any problem that seems impossible is now possible. All right, and so that gave us about 30 images in OpenMV Cam. And finally, we want to take 30 images of the background. So it's very important when you're doing a neural network that you have some number of classes. If you have like all the classes you want to find, you always have to have a neutral class for the neural network. If you don't give the neural network a neutral class, then it's going to be forced to classify the world into one of the classes you don't want it to be in. And the reason for this is that we softmax the output of the TensorFlow network, so it's always going to choose one option. It's never going to have not something it's classifying things into. And so we want to have a background class, which is just going to be about 30 images of the background. Okay, great. And so we have 30 images of the background. It's not really important that these look different from each other, but it is important that they have the same number of images on average of the other classes. This is so the data set is correctly balanced and weighted appropriately. If you only gave it one image of the background class, it would heavily not want to classify anything as background. Great. So I'm just going to wait a bit there. And how's everybody doing on taking pictures? A good feeling everyone's like at the same rate. Good to go. Okay. So any questions? I'm going to wait until I'm going to give us 5 minutes for everyone to catch up. If anyone has, if anyone's behind. Oh, we're getting a lot of good to goes. Okay. All right. Well, then let's. We can load up Edge Impulse next. Oh, how to remove 31 image. Just select the image in the editor and click delete on it. And then the IDE will give you an option to delete it. Yes, the webinar is being recorded. And then also the folder that I gave you with the workshop script has videos of me doing this, along with a script that has step-by-step instructions on everything you need to do around. All right. So the next step is we're going to upload this data set to Edge Impulse. Oh, yes. For your picture, Zuriel, did you focus the lens on the camera? It might have come out of focus. You should repeat the process then of collecting those data set images if the lens was out of focus. You can focus the lens using the Hello World application. All right. Okay. So the next step will be going to Edge Impulse and going to the online editor for that. So everyone, you should sign into an account on Edge Impulse and create a new project. You can use a GPU to do everything on board your own machine of TensorFlow. The trick is most people don't know how to do that nor have a powerful enough machine to do training themselves. So we offer Edge Impulse as a realistic method for most people to actually get work done. The OpenMV Cam though runs standard TensorFlow models, so you can create whatever type of model you feel like on your own machine. Yeah. All right. So yeah, for Edge Impulse, you basically log into an account, you create a project. Edge Impulse is nice, and there's really not that many options when you create your own account. Once you're on board there and create a project, the project will have no data in it, and it'll have a few different things you can do to get started adding data. The reason why we partnered with Edge Impulse to make all this go was it offers a realistic method for most users to actually train a neural network. It's particularly hard to get a laptop or machine with a GPU and installing all the necessary Linux tools correctly to train a system without having folks get stuck with the wrong setup and being out of luck. It's easy and only takes a weekend if you're very dedicated, but for most folks, this is impossible. So Edge Impulse offers a realistic way for folks to train neural networks in an easy manner that's not too hard. In particular, imagine a classroom-like environment where kids don't have access to a GPU machine. Edge Impulse is the only way they can actually get, access to training their own neural networks. Anyway, so luckily we've integrated OpenMV IDE into Edge Impulse. OpenMV IDE talks the same language and same API in order to upload data directly to Edge Impulse. And so the way you're going to do that is you're going to go, when you open up your project, you're going to go to the keys option. And this will give you a few things that you can see here. In particular, we want to grab the API key, and we're going to copy that, okay? And once we copy that API key, we can then go back to OpenMV IDE, and you can go to Tools, Dataset Editor, Export, and you can upload to Edge Impulse by API key. Now, if you've done this before, OpenMV IDE will have another API key with whatever previous project you had uploaded to already stored there. You want to delete that, paste the new one, and click OK. And once you do that, OpenMV IDE will then connect to Edge Impulse. Now, if you are on a network that has SSL sockets blocked to Edge Impulse, or if your computer operating system is blocking SSL connections from applications, that step that I just did where I clicked OK, and then you see this little box here would have failed, and you'll get a warning box about an SSL connection not being able to be established. These are issues that have to be fixed on your own end. It's not a problem with the IDE. We've had users in China suffer from this where they cannot connect to external services that haven't been like whitelisted. In America, it seems to be fine, but hopefully you can get around it if you have that problem. Anyway, once you get this little picture here, this is going to be the data set split. So pretty much you can split your data between test and training data. Training data is used to train a network, and then test data is data it's never seen before that we're going to use to validate it. The default 80-20% split is what you want to leave it at. Let's just go ahead and move forward with that number. After you click OK, OpenMV IDE will upload all these images to the Edge Impulse account. And once it's finished, if you have OpenMV IDE 2.6.4, it'll give you some upload statistics about how many images were uploaded, how many responses you got back from Edge Impulse, that the image was uploaded successfully, and then how new images and how many images were added. If you try to upload the data set again, for example, Edge Impulse does detect duplicates and will reject and not accept those images as new images. And that's useful to know if you want. This allows you basically to add to your data set and make it larger and bigger and do et cetera with it, and you don't have to worry about duplicates appearing. Yes, so this is how you configure the key in OpenMV IDE. You're going to go to the dashboard on your Edge Impulse account. You're going to go to Keys, and then you're going to double click on the API key. You're going to take that, you're going to go to Tools, Dataset Editor, Export, and you're going to upload to Edge Impulse by API key. And then you're going to paste that API key in and then press OK. And then just click through the dialogues, and OpenMV IDE will upload that data to your Edge Impulse product. Take some water. All right. So once we've got our data uploaded to Edge Impulse, you should be able to go to Devices, and you should see a picture of OpenMV IDE and saying that it has uploaded data. And if we go to data acquisition now, we should see that all of our samples have been uploaded to Edge Impulse. So we've collected 104 items. There's 4 labels. Yes, you can, Dimitar. You can upload directly from the Edge Impulse page. It'll be a little bit more involved on doing the upload, but you can do that too if you want to. We built this into the IDE so that it was super trivial to do it and not so intensive of you manually selecting things and uploading them. But you can go ahead and do that too. OpenMV IDE stores the data set as just a bunch of pictures in file folders, so it's pretty trivial to go ahead and upload these images yourself manually. All right, and so now we're going to have a bunch of pictures of these screwdrivers. Cool. And we have the Portenta, and we have the OpenMV Cam, and we have the background. Awesome. And so you can see our data set is roughly balanced. We have 4 labels. The pie is split into 4 mostly equal slices. And then you can see also we have test data. And test data is not balanced at all because we did not collect the same amount of items. Luckily, it's okay for test data not to be balanced. Training data, though, is very important to have been balanced. All right. moving along, the next step is impulse design. So Edge Impulse basically will allow you, without having to write any code, to design the neural network architecture that you're going to use, which is very, very nice. And so we're going to use a network with a 96 by 96 pixel input window. If you want to run your network on an OpenMV Cam H7 regular or a smaller system, you can shrink that network input size to about 48 by 48 pixels, and that'll appropriately shrink the network and make it faster. Of course, it will also mean the network can see less, and so it'll make its, the accuracy go down a little bit. And then for the resize method, we're going to click Fit Shortest Axis. So the default resizing mechanism that the OpenMV Cam uses is that it's going to crop the image to some multiple of 96 by 96, and then fit the area in which it's looking at the image into the center part of whatever that multiple of 96 by 96 is. So for 320 by 240, it's going to kind of look at the center 240 pixels, and then it's going to shrink that down to fit into 96 by 96 pixels. Next, we're going to add a processing block, and we're going to click Image. So Edge Impulse is mostly made for audio data, but they added an image feature, and it's recommended here with a little star. So you need to click that for this image data. And there's really not a lot to do on the image processing block. It has the input axis of image, and it's already pre-checked, so you're good to go. Next, we're going to click Add a Learning Block. So there's a few different ways you can go through adding a learning block. K-means and neural network keras are these are options for folks who are going to be hardcore programmers and know what they're doing. For everyone who's kind of, this is your first data set and first TensorFlow model, we're going to go with transfer learning. And this is basically going to use MobileNet v2 that was trained originally on ImageNet by Google. And we're just going to do transfer learning with that, which is a very quick process in order for it to be retrained to detect the random objects we gave it versus the image data set class. Anyway, so once you click there, the output then is going to be 4 features, which is background, OpenMV Cam, Portenta, and screwdriver. Once we're done, we're going to click Save Impulse. All right, so our impulse has been saved. The next step is we're going to go to image. So for the image feature, what's going on here is the raw features are actually all the pixels in the picture. And we're telling the system that it's going to take the color depth of RGB for all these raw pixels. And that's the raw data then that's going to be fed to the neural network. And notice that the image is being resized with the Fit Shortest Axis option here. What the Generate Features button does is it creates a database for the neural network. So we don't actually train the neural network on all the raw images. We first convert that into a very optimized format that we can quickly retrain the neural network on. And so this step we're doing right now is basically building an image database. So once you've gone in the parameters, and you don't really need to select anything by default, it's fine. You're going to go to the Generate Features button up on the top. And we're going to click the Generate Features button. And so what this is going to do is start up a batch process that will take in all the images and basically create that nice optimized database file for the neural network to be trained on. So that's getting run. It's going through, putting these things together, getting a job in the cluster. All right. Hey, Jürgen, you get the API key by going to Dashboard. Hold on, let me wait for this to finish. Okay, you get the API key by going to Dashboard, Keys, and you click the workshop key right here, and you're going to copy and paste that, and then you're going to go to Tools, Dataset Editor, Export, Upload to Edge Impulse via API key, and you're going to paste the API key into there. All right, so we're going to go to Image, Generate Features, going back to that tab. Okay, so if you've successfully generated the features for the image, you're going to see this crazy diagram. And that's showing like a scatter plot of how your images look when mapped to a three-dimensional surface. Daniel, can you actually elaborate more on this picture and what it means exactly?
Yeah, so hey everybody, nice to meet you all. So I'm the lead TinyML engineer at Edge Impulse. And so I'm here for extra info on any of this stuff if we need it. And the Feature Explorer, basically what we show here is we try to give you some kind of visualization, visual understanding of how your data maps to the or how your data is going to be separable by a neural network. And it's not always easy to do this with complex data. Some kind of signals, you can just look at them by eye and say, hey, this is really easy to discern from something else. But with vision, it's a little bit more challenging. So what we do here is we take, we have a special process that we can feed all of the data into, and it basically maps that data into a high dimensional space. So each data point, each image is represented by a vector in that space. And then we can plot those vectors on visualization. And so you can see here, some types of things are clustering together. So if you look up near the top there, we have all of these background images clustered together in a group. And then we have other places where there are little groups of portenta. There are other places where there are little groups of screwdriver. It might not be sort of super easy that you can just draw a line around it, but deep learning networks are basically incredible at learning to distinguish between these types of things. So the visualization here, the thing that's nice is we can see that there are some clusters of groups of images. Each dot represents one image. There are some clusters. There's some space between them. What we would want to be looking out for is like, are all of these just completely randomly mixed together, or are they all compacted together in a big blob? And if that's the case, if they're all just in one big dot in the corner, that would suggest maybe there isn't that much difference between the images that we can pick out. So yeah, Jeff says it's a picture that's worth 1,000 words, and it really is. It's a cool way of being able to explore a really complex data set with a fairly simple visualization. Yeah,
and I would add that depending on the network style you see, for example, I've seen that you have very obvious separable items with more pictures. Sometimes that there are very clear arcs of pixels where they're very separated already in this three-dimensional data space. And this picture gives you a good this gives you a good idea right off the bat that you're going to have success with your neural network. It works better with more items. So if you have like close to 1,000 images in the data set, it'll give you a very clear representation of how separable that data is. And if you see all the dots are right on top of each other, it's highly unlikely your network is going to solve the problem. But if you have like 1,000 images and these dots are spread all different ways, then the network is going to have a very easy time splitting that data. And so it's just going to give you a good upfront guess on whether or not the network is going to succeed. For this small data set that we're using right now, just 100 items, the network is going to probably just do a good job just because it's so easy. But for other data sets that are much harder, that you're probably going to want to train yourself, this will give you a good first-hand pass to let you know, is this going to be challenging?
So a good thing to mention is that if you're interested in like how on earth does this work, it's actually a tool called UMAP, so UMAP. So if you look that up after the talk, you can read about how that works. It's a sort of standard thing used by people who work with large amounts of data and need to visualize it.
All right.
I noticed, sorry, there's also a question from Ram, which is Edge Impulse going to be paid subscription to use with OpenMV, or will it always be free? So Edge Impulse is always going to be a free developer tool. So we have really awesome enterprise features that you can use if you have a big team working on massive data sets. And so that's how we support providing a free developer product for everyone else.
For Aditya, can we integrate OpenMV ID with other IoT products? Oh, the tool is called UMAP, Vitero. For Adita. So the OpenMV Cam features a Wi-Fi shield right now that can do basic sockets, and you can do pretty much whatever Python socket programming you want. Obviously, though, this is pretty popular, but it could be way more integrated. And so the Arduino Portenta is basically the the thing that we're going to be working on supporting. That will be the platform of choice for IoT. So Arduino has put a lot of effort into making that low power. It also has Wi-Fi and Bluetooth on board. We are supporting the Wi-Fi and Bluetooth stacks in our firmware natively, and you're going to be able to hit about 50 megabits a second moving data through the Wi-Fi shield. 50 megabytes a second. Additionally, well, no, you can't hit that kind of speed with the Wi-Fi stack. So whatever, it's going to be fast. And it also has low ROS support. So that's really going to be the way that we see people really doing IoT applications. But on the second half of this presentation, we're actually going to be talking about how you can use our OpenMV Cam interface library that we finished building to connect to an Arduino. And this means, of course, that you can connect an OpenMV Cam to an ESP32, you can connect it to an ESP8266, you can connect it to an Arduino IoT shield, you can connect it to an Arduino 33 BLE, whatever. So even if our support for networking is not good enough, you can always just have another processor do that and let us be a camera sensor. All right. So finally, the main step now. The whole purpose of doing that image tab there was to create the database by which we will train a neural network. Now we're actually going to train the neural network on that database. And the database is necessary to make in such that you can train the neural network fast. Like what the database does is that has all of the resized images in it that have been converted to the right color and cropped and everything. And then that database is also built in a way where it's very, very easily accessible by the training system for the neural network. Next, we're going to train the neural network now. So there's a few options here. If you want to go have Keras fun, you can switch to expert Keras mode, and you can get right into writing Python Keras code. You can also edit it as IPython notebook. Anyway, otherwise, if you're a more basic user, there's a simple GUI web page here. And so you just select the number of training cycles, the learning rate, and you want to click data augmentation. That'll make your network a little bit more robust. The default confidence rating is fine. And then there's also one other option where you can edit the number of neuron outputs. That will affect the smartness of the network and how large it is and how fast it runs, but at potentially decimating its ability to think. So there's a whole bunch of stuff here you can play with in order to tune the neural network. The default settings have been picked out by Dan, and they're pretty good to go right off the bat. So once you've got that, click the Start Training button. And here's the beauty. Edge Impulse has a whole bunch of GPUs in the cloud that you don't have to have in a box in your closet or room. They make it a lot easier to work with. You just click the Start Training button after you've uploaded your data, and you will get a neural network. I know of myself, after trying to do this with our previous CMIS-NN framework, that if you don't have a NVIDIA 1080 Ti, this does not take 1 minute. This takes on the order of 5 hours or something. And so it's amazing that they're offering this kind of feature for everybody. Because literally I just click that Start Training button and we have a model and we are done. That was fast. And our network is basically getting a 90% accuracy right off the bat for this simple 3-4 data set class.
Yeah, and I can jump in with some more info here as well.
Zuriel, try clicking it again. Well, maybe it's they ran out of. Dan, can you comment on Zuriel's issue?
Yeah, let me look into that. That is not what's supposed to happen. 1 second. If it is, it will be sort of a slash dot effect. So if you wait a few moments and try again, then it should work. Someone can be the first to grab Kwabena's worker when his training finishes. But yeah, this is something that we'll take away and look at.
Ah, okay. Yeah, I guess we do have a lot of people all at the same time clicking the train button. So.
Yeah, so if we keep staggering it, we'll be able to get everyone's model trained. And then this error shouldn't come up anyway. We should have the scheduler catch it, but that will be fixed by the end of today. I've kicked off a cascade of Slack messages from our engineering team. So a little bit more info about what's going on here. So we have the type of deep learning that's happening here is a thing called transfer learning, where we have a base model that was trained to recognize a lot of different stuff. And then we're customizing it. We're kind of tailoring it to work really well on our own data set. So that helps us speed up training a lot, and it makes a more accurate model as well.
And this is based off of MobileNet v2, which is a pretty high performance neural network trained by Google originally. And so you were leveraging, it's pretty state of the art models for this particular system. And one nice thing about Edge Impulse is that it outputs a quantized model already, which is very helpful. Daniel, do you want to talk more about the latest training performance diagram here and what all these things mean?
Yeah, absolutely. So we give you kind of a snapshot of how your model is performing and how it's going to potentially perform on device. So first of all, on the left, you can see your accuracy, which is basically the percentage of classifications that the model gets right. And then loss is a sort of numeric expression of how different the answers that the model gives, the probability outputs that the model gives are from reality. And so you can't compare loss numbers between different data sets, but for a particular data set, you can compare loss numbers. And so if we were to train another version of this model, we could use that to compare which one is better. So in the middle here, we have our confusion matrix. And this basically gives us a kind of comparison of the actual classes versus how the model has classified them. And so you can see here, we've got a nice diagonal across the middle of bold numbers. And this is saying for most of the examples, our model classified correctly. It was just for the portenter and OpenMV got mixed up a little bit there. So if you hover over that too, Kwabena, it will tell you the actual label was the OpenMV Cam, but 2 of the samples got predicted as portenter. So that gives us a bit of information. It's like, maybe we need some more samples in our data set of the OpenMV Cam and the portenter, and that will give our network a bit more chance to learn the difference between them. So on the right here, we've got some estimates for performance. And I believe if you hover over the little question mark next to on-device performance, this is for a Cortex-M7. So we're saying that each inference is likely to take about 1.2 seconds, and we're going to use 297K of RAM, 585K of ROM. So that gives you a good idea of what performance is going to be like for this when it's running on device and how much resource it's going to take.
Now, this is for a Cortex-M7 at 216 megahertz. The H7 that you're using is beefier in a few different ways. So first, the H7 is faster, but then something that most people don't think about, which is very important, which is the H7 has a larger bus width to the main RAM. And if you, for example, run a model on a H7 or on a M7 processor on like a Atmel chip, for example, you can think all the H7 models are the same. The M7 cores are the same, but the bus width to main memory definitely makes a difference. For ST's H7 processor, they used a 64-bit bus, and so it'll generally get 2x the performance of other Cortex M7 processors that have a 32-bit bus to main memory. Sounds like you got good result, Goran. That's pretty decent. It should work fine then in operation.
Yeah, so a quick note on stuff like accuracy. So neural networks and machine learning in general is kind of a probabilistic thing. The network's never going to tell you a definitive exact answer, and they're unlikely to get things right all of the time. And so when you're seeing accuracies in the 80, 90, 90 something range, that's generally pretty awesome. For some stuff, you can get super high, but generally you want to use machine learning on problems where a little bit of uncertainty is okay. So that's something to bear in mind when you're training models. But if you're not getting accuracy that is good enough, there are things you can do. You can add more data, you can use different model architectures, you can increase the size and shape of your model so it has more capacity to learn. So there are a bunch of different levers you can use, but it's important to be satisfied with accuracy below 100% because it's very uncommon to get full 100% accuracy all the time.
Oh yeah, you actually don't want 100% accuracy because that usually means the network just overfit itself and literally did not even learn the data, but it memorized the data set. And it'll usually have terrible performance in real life actually if it's actually at 100%.
So what we'll see, is when if you run model testing and it runs the model on your test data, then you'll see that the accuracy will be a little bit different. Because it will perform different on data that it hasn't seen before.
Yes. And then for RAM, so I don't know what the performance numbers are based on, but on the latest firmware for the OpenMV Cam, we did enable CMSNN. So that was broken forever, by the way. Finally, thanks to the help of Edge Impulse, they actually got through some pernicious bugs in the TensorFlow Lite CMSNN code. But John at Edge Impulse went in there and found some pretty heinous stuff and fixed them, and that finally enabled TensorFlow Lite to work with images. And so once that was fixed, we instantly integrated that into our firmware, and so we have a 4x speed boost now on all neural networks produced by Edge Impulse, and so you should get some decent frame rates after you run these networks that we're about to download.
Yeah, so there was a question earlier about what's the point of Edge Impulse if you can just run this yourself? So the thing is, we have a whole team of really absolute experts working on this stuff, and it's still hard to get right. So of course, Edge Impulse is built on open source technologies. We use sort of the cream of the crop of open source technologies from companies like Google and ARM and so on. But sometimes integrating things and getting them to work together smoothly can be really hard. And a lot of the value of our platform is that we've gone through all of this difficulty for you. And so when you integrate or when you export your model for OpenMV, it's just going to work. You're not going to have to deal with some crazy bugs in some open source libraries.
Yep. And then Dan, can you comment on is the performance numbers based on CMSNN optimizations or just using the TF reference kernels?
Yeah, it should be with the CMSNN optimizations. And again, if this number, oh, sorry, go ahead.
No, go ahead, Dan.
I was going to say, if this number is too big for you, basically the bigger a model is, the more time it takes to execute. And so if you want to make a model that runs faster, you can choose a smaller one. So you can either, with transfer learning, you can choose a different transfer learning based model. If you're defining your own model, you can make sure it has less layers. You can do stuff like reducing the input sizes, so the model's dealing with less data. And so this is going to lead to faster execution, but there can be a trade-off where your accuracy goes down. So part of the thing here that you do as a domain expert is what an acceptable latency is, what an acceptable accuracy is for the task you're trying to do. So you can then adjust things within Edge Impulse to find the correct balance of those for the problem you're trying to solve.
Yep. And that's the beauty of this tool. You can also do things like adjusting the neuron output. That'll instantly cause the model to go faster, but it'll significantly handicap its intelligence. Cool. So then we can go to model testing. And so if you want to actually see what the real result is on how well this thing does, we can classify these selected 17 images and model testing. And hopefully we gave everyone enough time to get through the Edge Impulse being hit by so many people trying to train at once. Okay, and so the actual accuracy of the network is 94.2, so 94.12%. It only failed to classify one thing, and it was uncertain on seeing if an OpenMV Cam was an Arduino or a Portenta, which we already got some information beforehand on our confusion matrix. Boom, so the network is going to do good. All right. And then before we move on, Dan, do you want to comment on some of the things I skipped over here real quick?
Yeah, sure. So some of the things that you can do in Edge Impulse beyond just training your model are managing different versions of models. So if you're iterating and trying to find the best possible model, you can take a snapshot of your work at a certain point. You are able to use actually some really cool features for data acquisition. So if we use OpenMV Camera to grab all our data today, but you can also add your own devices and even connect your smartphone so that you can take pictures and add to your data set that way. You can upload data through all sorts of mechanisms. I mentioned in the chat, there's an upload tool in the web UI. There's also a command line tool that you can use. And we have APIs for literally everything that you can see in the tool here. So if you want to automate your flow, you can do that. So Kwabena here is showing off the upload UI that you can use to basically grab those images and dump them into Edge Impulse from the browser. Another thing you can do is in live classification, you can check any sample and look at the exact performance. So if you click load sample on classify existing test sample there, this is going to show the exact probabilities that the network returns for this sample and then how it classifies. So you can see it actually just knows for sure this is a screwdriver. So there's a probability of 1 for screwdriver. But for some things, if it's a bit less certain, there might be a probability distribution across the 4 classes. And you can see here in the visualization where this sample fits. So if you find a sample which is classifying wrong, you can go and look at where it appears in the visualization. And sometimes that can help you spot bad data. Maybe a picture of the wrong thing sneaked into your data set. And using this kind of tool, you can easily identify that. So I think the rest of the really interesting stuff is on the deployment tab. So I'll let you get back in the driving seat, Kwabena.
All right. So what is nice about Edge Impulse, and this is probably going to appear in the future for us, but is that Edge Impulse doesn't just create a OpenMV TensorFlow Lite file, it also will build firmware for you. So if you're serious and running a company and want to deploy firmware to a device that has the neural network baked into a firmware, along with all the other drivers and et cetera, Edge Impulse will create that firmware-based application for you. That can be either a C++ library, an Arduino library, a STM32Cube AI stack output, or ready to go firmware for a board. And so in the future, for example, you'll be able to do things like create an Arduino Portenta firmware that has all the drivers and your neural network all baked into the flash. And you can just supply the Python code on the top layer to connect everything together and work the way you need to work. For this particular example, though, we're going to just download a TensorFlow Lite file for the OpenMV Cam, and we're going to store that on the QSpy flash on your OpenMV Cam. This is not as good as having custom baked firmware because we still have to load the network into RAM versus if the network was baked into firmware, there's no RAM loading part. You can directly execute the network from memory mapped firmware that's on board the microcontroller. All right, so we're going to click the OpenMV library button. We're going to select that, and then we're going to click build. And what that's going to do is it's going to spit out a file, the EI Workshop OpenMV zip file. Awesome. Okay, so once you have that, you can open that up. I'm going to pop that open with WinRAR. And I have my, so if you have your OpenMV Cam H7 connected to your computer, it should appear as a flash drive. So the OpenMV Cam H7, by the way, has a 32 megabyte Quad SPI flash on board. And that Quad SPI flash is mapped as a it looks like a flash drive when it's plugged into the computer. We built the OpenMV Cam H7 with this Quad SPI flash in particular in order to enable you to just drag and drop neural networks on board it without having to worry about does it fit. That's the whole point of this. What's nice about the Quad SPI flash is that it has a 50 megabyte a second read speed. So it is very, very quick for reading data off the Quad SPI flash and sucking that into the microcontroller. The write speed is pathetic though, at about a couple kilobytes a second, because Quad SPI flash is not at all optimized for writing, it's optimized for reading. But from your perspective, it doesn't really matter. All you have to do is copy the trained.tf Lite file and labels file to the disk and say replace, and Windows will write those over. And as I mentioned, the write speed is mad slow because it's Quad SPI flash. It is not optimized for writing, but it will still go through Windows easily. All right, once that is copied to the disk, boom, our neural network and the labels.tx file. The labels file has all the labels that we use to train the network. That's how we get the label from, the network itself is just going to output a classification score, a index. It has no concept of what that index actually means in real life. So we have to have a labels.txt file that maps that index score to an actual numeric, alphanumeric lettering of what that particular class score represents. Anyway, so once we've got that on board OpenMV Cam by copying it to the onboard Quad SPI flash, we're good to go for running the network. All right, so now we can close this. Oh, excuse me. And one more thing, the Edge Impulse script will also, Edge Impulse will supply a script to run all this stuff if you need to in their default download. Okay, so we're good to go then. That's all that we wanted to do with Edge Impulse. And so now we are going to go back to our script that's running on board the OpenMV Cam. We are going to stop that. And we are going to switch open the Edge Impulse classification script that you should have downloaded. You can just drag that from that zip file into OpenMV IDE. OpenMV IDE supports drag and drop, and that should open up. And now we're going to click the button to run it. And let's see what happens. Put a screwdriver in the field of view. And we can see that the classification score for the neural network now went to 97% there. And if we want to have a numeric label for these classification scores, I'm just going to copy some code from something else to make this a little bit more. Let's not do that right now. Okay. All right, so basically in the serial terminal, we can see the class prediction outputs. First, we can see that the network is running at about 4 FPS. This is thanks to CMSNN that we're able to achieve that level of performance. Anyway, and so you can see the different classes that are there. And so right now, the network has a confidence of about 97% that that's a screwdriver. Let's put another screwdriver that's never seen before, a yellow screwdriver. And would you look at that? It still has a 85% confidence that that's a screwdriver. This is interesting because note that we've never showed it this picture of a yellow screwdriver, and the network is actually identifying the screwdriver based on its screwdriver-ness-like properties. It's not doing it based on color, which is something we would have had to previously do with an OpenMV Cam using color tracking. Let's put Arduino Portenta in front of the camera. As you can see, it is 100% confident that that is a Portenta down below. Now it's 94% confident, 100% confident pretty much, and 83% confident. Finally, let's put an OpenMV Cam in front. And it is 100% confident pretty much that that's an OpenMV Cam. Now it thinks it's a Portenta though, when I put it to the left-hand side of the screen. So we can see right now then we're missing some data on having the OpenMV Cam located in this area of the field of view. And that's where we're getting trouble with the network. It's not actually generalizing on where that object is located. It's kind of thinking that if it's in a particular area, it's a particular object. So this is where we want to add more data to the model in order to improve its performance. So by the way, you can see the class score right down here for the camera. Awesome. And if we put nothing in front of it, it thinks it's a background at 96% accuracy. All right. And so this is what's cool. We just trained a neural network in 30 minutes that identifies random stuff on your table with very little effort. And so now you can imagine, what can I do in real life for a particular application and train a network on that? Really all it involves is going out and collecting a robust data set that has examples on everything you need, making sure to prune out the any wrong objects in that data set that don't belong, and then training a network and refining it. And by doing this iteratively, you can produce a high quality data set that will be able to identify whatever object you need in a timely fashion. And obviously, if you were to reduce the network to a 48 by 48 pixel network, you would appropriately get about a 4x speed boost, getting this going to about 16 FPS from 4. Any questions? How's everyone doing? All right. Yeah. Hope this is actually blowing everyone's minds as much as it originally did for me. The OpenMV IDE connects to the terminal over USB, so the baud rate's effectively 12 megabits a second between the camera and the IDE. And then with the Arduino Portenta, we have up to 480 megabits a second through USB 2.0, finally. So it's that doesn't really matter what the baud rate of the terminal is. Is this usable for face recognition? You can. I would say, though, it's probably not going to work the way you think. Dan can give some more thoughts on that.
Yeah, so what we're doing here basically is training a model to recognize different categories of item. And so if you had, for example, 3 different people and you trained a model based on data captured from those 3 different people, like a lot of pictures of each of those 3 different people, you could potentially train a model that could distinguish between them. However, that's not how commercial face recognition solutions work. So they work using a completely different type of model architecture, and essentially they, rather than needing like dozens or hundreds of photos of someone, they can take a single photo and sort of figure out a mapping of that particular face into a giant n-dimensional space, and then look up in a database which people that is close to. So it works very differently. So you can approximate something. If you were just building something for like using in your home to recognize yourself versus your partner, that's totally doable. But with this flow, you're not going to be able to build like a general purpose face recognition system. And you wouldn't want to build something that like opened your front door or something based on recognizing your face, because what you can do is distinguish between 2 people, but the network's going to have to then figure out which of those 2 people the other people it sees look most like, and it will always choose one. And so this isn't the right tool for doing proper robust face recognition. You can do person detection, where you're recognizing whether a person is present in the picture or not, which is really cool for a lot of stuff.
We actually have person detection baked into the firmware on all OpenMV cams because it's so awesome. So that's built into, we actually have Google's visual wake words dataset, visual wake words model that does person detection. And so on all OpenMV cams baked into the flash, about 285 kilobytes of flash data are used to support Google's person detector network. And that's an example of a network that's baked into Flash. It runs very quick. But what we'll be able to do in the future is we hope to kind of have the option that you could eject that network out of the Flash and put your own network in instead, and have kind of like Edge Impulse automate that flow of generating a custom binary. And this is going to be done in partnership with Arduino once we get to that point. And then we have a few questions in the terminal. Someone had error access denied, Zerial. So there's 2 methods of making a terminal inside of OpenMV. There's an open terminal feature. That's for creating custom terminals to whatever, because I'm a coder and I felt like I needed to have some sweet serial terminal action. And I realized most serial terminal programs are kind of bad. So I actually added sweet serial terminal action into OpenMV IDE. But that's separate from the main terminal, which is connected over through a different mechanism. And then if you're having access to that when connecting with the main terminal, it's because you're probably on a system that prevents dial-out access. So you need to add yourself to the dial-out group in Linux and then log out and then log back in again. So that's something you can't fix right during this call. That's a common problem that a lot of people have with microcontrollers using serial ports on Linux, starting off. And then, let's see, multiple objects at the same time. Can you comment on that, Daniel?
Yeah, absolutely. So there's a couple of ways you could approach this. So if you wanted to determine, is there a cat and a dog in this picture? Or is there just a cat? Or is there just a dog? You could, using the same flow we've done here, just collect different classes for each of those options. If you want to do something that's a little bit more like what you might have seen online with object detection and localization, where you might have a cat in one corner and a dog in the other, and you draw a box around each one and recognize what it is. We don't support that in Edge Impulse just yet, but it's something that we're working on. And interestingly, you can kind of approximate that with regular classifications. So the way that you do that is, imagine you segment your screen into sections. So you could segment this into 6 boxes, and then you train a model that can classify whether a cat or a dog or nothing is present. And then you just split your image into those boxes and run each little box through the network and get a reading for each one. And we're doing 3.8 frames per second. So in a little over a second, you're going to cover all of your boxes. And that will give you an understanding of like what the probability is of each item in each box. So you can kind of approximate that already, and we're going to be working on adding those types of features to Edge Impulse directly.
Yeah, just for future expansion notes. So what we want to do, so in OpenMV IDE, we plan to extend the dataset editor to allow you to open up images and then draw bounding boxes and et cetera around them, and actually do pixel segmentation by, like, you know, painting on an area, being able to define a pixel segmentation mask. And then this will allow you to build a data set inside of OpenMV IDE that can be then uploaded to Edge Impulse to train a network to do pixel segmentation on objects and bounding box recognition. And so that'll come in the future. Right now, we just rolled out image classification because it's by far the easiest to support. But you know, once we have time and to work on getting these other networks down into hardware, it's really going to blow people's minds on what you can do. And then regarding the splitting the images into different sections, so the classify function, by the way, supports something called, it supports multi-scale detection. Basically, the classify function walks over the image and will scale the, using the X and Y overlap options, it'll basically overlap the bounding box by X and Y percentages on the image, and then it'll scale down the image every time it finishes iteration through X and Y by the scale multiple, down to the minimum of min scale. By default, we have min scale set to 1, meaning that it gives up after the first iteration. But if I, for example, were to change this and set that down to 0.5, then the network will all of a sudden run multiple times, and it's going to take a while, but you can see the network is now running more than once, and it's rescaling the image and then running the neural network on all these different pictures there. And if we change the overlap from 0.5 to, let's say, 0.9, for example, then the network is going to slide itself around, and it's probably going to run for a very long time. So give it a sec. It's very easy to obviously hit the computational load, but there's an example of the network being run on a whole bunch of times on the image and rescaling it. And so that's kind of built into the OpenMV IDE by default. As we're seeing, though, it's basically taking it about 10 seconds to run that neural network when you do that. So be very careful about adjusting those parameters. The default ones are pretty good. For Pituro, we're using MobileNet v2. That's what transfer learning is starting on. And then for YOLO v3 and SSD, that's coming in the future. Right now, we're not there yet. MobileNet, Dan, can you comment on if MobileNet can support bounding boxes output by default, or does it have that ability?
Not the way that we have it set up right now. So we need to basically add that feature to Edge Impulse to be able to do that. So the way that what we do for our transfer learning based models is we took MobileNet architecture and we shrunk it down so that we've got 3 different variants of MobileNet that are kind of small, tiny versions, which we've tested and work on a range of embedded devices. So I think the smallest one is around 100K. And we pre-trained those on ImageNet. So we did that. That took days and days in our GPU cluster. And we got these ImageNet based models, and then those can be used to very quickly retrain on your own data set within the Edge Impulse Studio.
For Zuriel, you don't want to do tools open terminal. That's for opening a second terminal. The serial terminal, by the way, if you don't see it, you just need to click this button down here called serial terminal. When you connect it to the OpenMV Cam to stream data, it automatically establishes a image input and a serial console. The open terminal feature is so you can have more serial terminals. So if you want to have like 2 boards at once, or 3 or 4, or connect to some other random serial terminal device, OpenMV IDE just supports the ability to open up an infinite number of extra serial terminals to connect to random things. For C Kitchen, yes, the board does get warm. So we actually power the OpenMV Cam using the 3.3 volt supply to the STM32H7. On the new Arduino Portenta, Arduino is much smarter about this, and they power the STM with a 1.8 volt regulator source. Because most of the heat you are feeling from the OpenMV Cam right now is actually heat dissipated from the internal 3.3 volt to 1.8 volt regulator built onto the STM32. So the STM32 actually has a regulator inside of it that down regulates 3.3 volts to the core voltage. And we've always just been treating these as a standard microcontroller that you give 3.3 volts and have fun with. But for the Portenta, Arduino did a true low power design. So they feed the Arduino Portenta with a much lower voltage input. And that wastes a lot less heat that's being burned off from the voltage regulation there. So with it, you'll get much better power consumption numbers than our current board. And it'll be less warm. For Mohammed, it's really the detection method. So as Dan mentioned, no one's really explored the concept of can you get YOLO running on a microcontroller? And it's just been because YOLO is stupid huge by default. And so no one's thought about how do I shrink that down? So TinyML is really about pushing that forefront. What you're seeing right now with the OpenMV Cam running TensorFlow Lite on board is really like brand new tech. No one's ever really gotten to the point of thinking about, could we actually get this type of image classification running on these low powered systems? And so I don't think it's a stretch to say that in the future, we're going to be able to run bounding box detectors and pixel segmentation networks on a microcontroller. And this is of huge value because if you have this running on a microcontroller, all of a sudden, if you want to do overhead person tracking in every light switch inside of every light in a building at a very low power, that's possible. Chuck B has a question. I think it's for you, Dan. It's I mentioned that Edge Impulse is built for audio. Can you elaborate on that, Dan?
Yeah, so I hate to contradict you there, but actually we're basically sensor agnostic. So we did start out with a bunch of features for time series data, which includes audio. And that was sort of the place we started out. But we've basically, our attitude is that if you can give us data then you can train models with it. And we don't care what type of sensor it comes from. So we have a bunch of really cool high-level support in terms of things like firmware that can automatically capture audio data, accelerometer data, and image data for you. But with our SDK and our APIs and with all of our model training functionality, you basically just dump whatever data you have into Edge Impulse and you can train a model on it. So it's super cool. You're not even limited to doing a single sensor at a time. So imagine you have some data from an accelerometer. You've also got a magnetometer. I don't know what else, a microphone at the same time. And you can train a model which takes all of that data into account. So you could recognize what's going on in a fitness tracker, for example, based on all sorts of different stuff. So yeah, it's really, really super flexible in that regard. And we keep adding more functionality and adding more sensors and data types as we go.
Okay, to Ram, if I connect an additional camera to OpenMV Cam SPY pin, does the software support multiple cameras at the same time? Yes. In fact, you can transfer images between OpenMV cams using SPY, actually. We have a demonstration underneath File, Examples, Remote Control. And there's the image transfer raw between controller and remote device, where you can actually have one OpenMV cam sharing its frame buffer with another. But the software does support working with additional cameras at the same time. I would say it's not, the API isn't the best though, because it hasn't been our focus, but we're trying to work on, with our partnership with Arduino, we're really pushing, getting back to the basics and really making sure that we have all the input and output features people need. And then letting TensorFlow really be the thing that's going to be used for processing. And we're just going to focus on making sure the image library has all the features for I/O that folks need, and image conversion, scaling, rotation, lens correction, etc. For Dimitar, is it possible to export a C library with Edge Impulse? Yes, it is. That is an option on the deployment. You can do a C++ library, and that has no dependencies at all. So if you download that, all you have to do is feed it an image on your microcontroller of choice, and you're good to go. And then to Jeff. Yeah, so Jeff, to your question to find multiple objects, yes, you can do that. And some folks at SparkFun actually posted a video tutorial of them finding Lego bricks using this feature. It's mad slow though, but it is possible by using this multi-scale classification thing. You can keep track of which detection had the highest score and then store that in a Python object. And then once you finish iterating over all the objects, you can then just return the highest score. That's pretty trivial, just a standard loop over an array, find the max value, store it, and then keep track of that. Oh yeah, okay, Dimitar was asking if there's a C++, a C option. Danny, can you comment on that?
Yeah, so I posted a couple things in the chat, but basically if you're working with C, you have the option of building our Edge Impulse library with C++ and then linking it to your C program. So we have an example which I've pasted in the group chat of how to do that.
Yes, by the way, so TensorFlow, for example, is a C++ library. And so we had to go through a lot of like shenanigans with OpenMV to actually, convert that into C, because our firmware is actually in C. By the way, if you do want to have access to TensorFlow, here's a little post people might like. So let's go to OpenMV Cam. So we actually have a TensorFlow lib package for everybody. So our TensorFlow lib is on our GitHub, and this is a basically pre-built, so what Edge Impulse has is better, I would use that. But for OpenMV firmware, we have a pre-built TensorFlow library package for the Cortex M7 and M4 that include both the person detector model and a libtf.a. And the libtf.a is basically built in a way where we have some callbacks that populate image data and populate the output channel. And we tried to document it and make it as easy and straightforward for anybody to use to integrate TensorFlow into whatever microcontroller they want. And so you can also use this if you don't feel like using Edge Impulse's library. And there's a whole build script and everything that shows off how we took TensorFlow and managed to compile that. But Edge Impulse's output will probably be far easier to use. Cool. Let's see. Okay, great. Answered all the questions. All right, so now we got a little bit of time left. How much time do we have left, Rob? Or Carl?
I believe it's 15 minutes.
Okay, who wants to see it connecting to Arduino in 15 minutes? Because literally there's no code changes here. It's super easy. All right, so if you have your Arduino hooked up, and you can, by the way, again, go to our the Google Drive that we have that shows off this material. Just follow the workshop script. There's some examples in the workshop script of showing exactly how you need to wire things. And so you can just pop into there and lag. It has, where you can download things, and then it has some pictures of the hookup pins. So for this tutorial, I actually had the Arduino 33 IoT, not the BLE board. So I never actually tested the BLE board, but I did have one of our users confirm that it does work over SPI with the BLE board. So let's get started on that. So I already have the Arduino IDE open. So first, you're going to open up the image classification as the remote device script. You can download that from the Google Drive that I shared. Let me just share that link again for everybody to make sure everyone's got it. There's that link. Okay, so you want to get the image classification as the controller, as the remote device.py, and image classification as the controller device.eno file. So the eno file is what's going to run on your microcontroller, your Arduino 33 BLE, and then the Python script will run on your OpenMV Cam. So let's just go over this real quick to see what's going on. So basically, we created this library called the Remote Procedure Call Library for the OpenMV Cam. It's designed to be a super high performance half duplex communication library that works over USB, Wi-Fi, CAN, I2C, SPI, and async serial. So pretty much any interface you want, it works over. It could probably work over one wire too, but that's not really a popular interface anyone cares about. So not going to bother supporting it. But the whole idea is the RPC library is meant to move data over pretty much any interface. And moving data over SPI and I2C was particularly challenging to support. So anyway, this library is built to be a high performance remote procedure call library. So basically it allows your OpenMV Cam to act as a slave device, accept an incoming function call from the remote device, do some work, and then return high level data back to that remote device. It is not handicapped. You can return literally any length byte struct you want. So if you want to return an image, if you want to return a string, if you want to return a complex data structure, it can do all of that. For the Arduino though, it's pretty trivial to kind of overrun its capabilities. So we're just going to return a string. That's the easiest thing to work with. But if you are using the RPC library between two different Python-based microcontrollers, then you can get into all sorts of fun with high-level data structures very easily. All right. So let's just go through the script real quick. It's going to have the more or less basic template setup for running OpenMV Cam. And then the way RPC works is you define a interface. In this particular example, we're going to be defining a SPI interface that's going to use the OpenMV Cam SPI pins. And we're going to set the clock polarity and clock phase and the CS pin of P3. Our interface does support the ability for you to effectively, you can have a master on the other side that could connect to multiple OpenMV Cams at the same time over SPI if you wanted. So this is, actually utilizes the bus's properties. For example, you can have one master controlling multiple OpenMV Cams over I2C, etc. And then there's also a UART interface. You cannot use that for your Arduino BLE 33 because it does not have a UART. So we're just going to keep that commented out. If you have the Arduino Nano 33 IoT though, that does have a UART, so you can use that. And I documented that on the workshop script. All right. And then we have some canned TensorFlow code. This is pretty much the same thing as it's running on the Edge Impulse detection script. We just took that out and put it into a function. And then finally, we have some callbacks. So the way the interface library works is you register a callback to be run when someone calls it remotely, i.e. the controller device, and then you call the loop function, which goes and handles the whole RPC stack, which is complicated. It has, you know, all kinds of great stuff in there, CRC, data protection, et cetera. So it's a nice, decent quality data link. And when a callback is called, this callback being the object detection callback, it's going to take a picture and then run the detection code on it, and then return whatever string that outputs. And so we're just going to click the run button and put that on our OpenMV Cam. Okay, and then normally that won't start running by default unless you've already programmed your Arduino. So next we're going to go to the Arduino editor and we're going to open that image classification as the controller device Eno. Again, I've already done the script, everything's already configured, so you just got to open it. And then you just have to select the correct board. So I have a Arduino Nano 33 connected, so you should set the right board to whatever you're using. So if you have the Arduino Nano 33 BLE, select that. If you have an Arduino Nano 33 IoT, you need to select that. And then you're just going to upload. And if you don't have the right board managers installed, please see the workshop script after the workshop and go through installing the right board managers for your hardware, because you'll have to do all of that. And then to ROM, to try various TensorFlow Lite examples in OpenMV Cam H7+ board, do you recommend resource for code and documentation, please? Can you elaborate, Ram? Like the TensorFlow Lite examples, it's really through Edge Impulse. We really just have a person detector network on board. If you want to run the person detector network, you just go to File, Examples, Machine Learning, and TF Person Detector. That's really the only thing we support. And the reason for this is that really the whole concept of running the neural network on a microcontroller has not been explored. And thus it's pretty much impossible to run any larger neural networks on board the system. Through Edge Impulse, we're going to be bringing out the idea of being able to support other networks. So for right now, though, Edge Impulse is pretty much the place you want to go to train networks currently. All right. So if you hit the compile button and everything went well and it flashed your board, and then if you have it hooked up correctly, you should see in your Arduino serial terminal the classification results being printed out. And so right now I have, and we can just shrink that here. And so you can see what the OpenMV Cam sees, and you can see the Arduino is saying this is an OpenMV Cam. And you can see that it constantly confuses it between a portenta, if my hand's in there or something. So the data set on the OpenMV Cam is not quite enough. I think we're missing images in this quadrant of the picture. So that's definitely something we'd want to fix in our neural network classification library or image data set. But put a portenta in front of it and boom, the Arduino can see it. And so for our viewers who are asking about, could I hook this up to another system to do IoT? Well, we have an example showing off right now how we are connected via the SPI bus to an Arduino Nano 33. You can build an adapter board, connect these two devices, and now again, you can use the Arduino Nano 33 IoT, which effectively has the ESP32 on it for the IoT part, and go online, transfer data to the web, do whatever you want, have fun. And does it find a screwdriver? Boom, it sees the screwdriver. Does it see the other screwdriver? Yes, it does. Does it see background? Does see background. Does it see an OpenMV Cam? It does. And then Ram asked, in that case, does Edge Impulse have more TF Lite examples for the OpenMV to share a web link with us? So, I mean, the whole purpose of this RAM is that you can train your own network to do whatever you need. So, yes, you could find more pre-canned examples, but the concept was, instead of trying to run example networks, which don't actually do the thing you need, you just train a network from scratch immediately that actually does the thing you need right off the bat. Dan, can you elaborate more on that?
Yeah, totally. So if you have for example, a particular thing you would like to do, like first port of call for me is usually to think about, are there any existing data sets? So if you just look around, like do some Googling for data sets on particular vision problems, there's a bunch, from silly things like cats versus dogs through to more important things like recognizing different diseases that a crop might have on by looking at the leaves. And so if you have a data set that you found online, you can just drop those into OpenMV and upload them, or you can upload them directly to Edge Impulse and then train a model and then export that and have that running on OpenMV. So if you're looking for sort of stuff that's ready to go already, that's kind of the equivalent here. It's like, rather than thinking about the model, it's more that we're thinking about the data set. But like Kwabena said, the magic of this is really, it's so easy to train your own, capture your own data sets and train your own model with all of this stuff. And like the things that OpenMV does to make it easy to work with the inference once you've got this thing on device are super amazing. So if there are things that, if there's a, I don't know, just type of thing you'd be interested in learning about, let me know in the chat, or drop a message on the Edge Impulse forum. I posted the link for the forum in the chat. If there are particular things you'd like to learn how to do, let me know and I'll see if I can find you some resources and maybe even put together a little guide.
Yeah, the big idea though is we really want to let people get away from the concept of you know, examples are cool, but we want to enable people to actually do real things. And so this is all about enabling everybody to train their own networks on whatever data set they want. I think that's the big leap that we're trying to get for folks, is that we're trying to extract, like, when I search for how to train a neural network, I see tons of articles where someone is just gushing about downloading the tools, showing how they're writing this cool code that does it, and then trying to get a job. And those are the things that we want to get away from. We want to show people, okay, how can we actually do real useful work using this tool? How can we show off, okay, I want to take this data set, I want to create this model, and actually focus on the more high level problems of producing a model that does useful work versus focusing on trying to run a pre-canned example.
Yeah, that's a really good point. I think we've had this kind of culture in, because the tooling for doing deep learning has been so inaccessible and so difficult to use. There's a little bit of culture that's evolved around like, oh, is there a pre-trained model for this? Oh, it doesn't fit on my device. That's too bad. I can't use it. And people have been limited really to like the models that researchers happen to have created. And I can tell you one thing, this is going to change in the next year or two, but ML researchers don't care about tiny models. They've blinded by the fact that it's fun to have big numbers and fun to train big giant models on banks of GPUs that try to get the top accuracy on a particular weird data set that someone captured 10 years ago. So what we're doing in this space and what you're doing as developers working with this technology now is really charting new ground. When you train a model that distinguishes between a screwdriver and some dev boards on your desk, you're the first person who's ever done that, and you are charting new ground. Every problem you solve with this is solving problems that are in a blind spot of the wider ML research community. So you should get out there and try stuff and do things that no one's ever done before. It's not often that a field opens up like that. So it's a really fun place to explore, and you can get really good results that are ready to use in production applications.
Yes, and then as we mentioned, our goal is to kind of keep pushing this forward. So the next thing I think that's going to be easier for us to unlock is image segmentation. That'll be the most immediate, next easiest kind of network model architecture to support, because that's just really outputting a separate image class. It's basically just, instead of outputting a class number, you just output a class score per pixel, which isn't that computational. It's not that necessarily different than what we're currently doing right now. And then moving on from segmentation masks, we're going to be working on then doing bounding boxes. These things will come online in the future, but the hope is we'll have like, a network running on board the camera that will be able to actually segment an image and draw boxes around objects like how everyone wants nowadays. Thank you. Nope, we've got a few minutes left. Carl, how much more time are we working with?
You got 15 minutes left. I was wrong when I said 15 minutes before. You have 10 minutes left now. Let's say 12.
Well,
so enough time for questions, closing remarks. I feel like that was a pretty good place to end unless there are more questions.
I mean,
I wanted to say, oh, sorry.
Go, Dan. Yeah.
I wanted to say thank you so much for the fantastic questions. We've had such good questions in this session, and it really impresses me how people pick up this technology so quickly and start getting to the stuff that matters. So I'm really excited to see what this community is going to build with TinyML and OpenMV.
Yeah. So, I mean, we can probably end it on top of the hour, but does anyone else have anything they want to ask? Yeah, sure. Send me a LinkedIn connection, Will. Yeah, ask your question, Elson. A model that tracks movement. Okay, that's an interesting question. People have actually asked about that. So the way you do that is not the most straightforward way, but what you basically want to do is you want to take a difference image using the OpenMV Cam and then train your neural network based on that difference image. That's one easy way to approximate it with the tools we have right now. Alternatively, we want to be able to support a network that has memory. Actually, I don't really know how close we are to that being possible because our programming model doesn't really support memory in the network, but maybe Dan can elaborate on that for networks that actually have the ability to remember what's going on in previous frames. Dan?
Yeah, so some of this is sort of you can do in the application space. So you're, if you've got, for example, you're using this mechanism for localizing within the visual area where something is, you can figure out if it's moved over time. So it kind of depends what type of movement you want to track. Another thing you could do is, right now we've shown off how you can capture just regular images and train a model based on those, but you can actually do some like meta analysis of images before you upload to Edge Impulse. So imagine you created an image that was like a diff of what changed over a few frames. So that captures some information about motion. And we're going to see some cool things that I'm probably not even aware of right now. So imagine you've captured this type of diff. As long as it's an image, you can throw that into Edge Impulse and do the exact same stuff we just did. And in fact, even if it's not an image, even if you're capturing like time series of like which regions of an image were active, you can just send that into Edge Impulse too. So you don't have to just send in static pictures. You don't have to send in video. You can do some clever pre-processing ahead of time and use that to train a model and get some pretty good results.
So here's an example of me doing image differencing with background subtraction. So I'm subtracting out a static background and doing frame differencing. This is totally data that you could send, train a neural network on and send this to Edge Impulse. And this is the difference image then instead of being whatever the background is. So it instantly highlights the useful object and everything else is just black. Now, what you can do though, it's probably too much effort for me to code this right off the bat, but given these difference images, then you can accumulate them. So you could do basically a infinite impulse response filter, where you basically average images together, and by default with averaging of kind of blending those images together at a 0.5 blending. That'll keep basically 32 images inside of that difference image buffer. And you can imagine then as you blend those images together, they'll ghost. So like if you move an object, you'll see ghost trails of it through the image, and that can kind of track how object is moving basically. And then using that information, you can send a data set to Edge Impulse that's these ghosty difference images. The better solution though would be to have a network that has memory built into it. So that's something that we'd want to add support for in the future. I don't know what that looks like, but there's plenty of RAM on board the 8.7 Plus to have a buffer that stores some kind of network activation that's saved over across multiple images running in order to support that. For right now, though, you'd have to use some more basic methods of just building a data set up of like difference images and difference images that are blended together over time. Yes, Frederick, you're asking how could you create a bounding box. So what we're going to try to do is by having an image segmentation network, you can easily use something called blob tracking to group a bounding box over the segmented image. So that's why we want to go for that first, because it makes it very trivial to do bounding box tracking on objects. The full bounding box regression is a little bit more difficult because those can sometimes overlay on each other. But these are all things that we're going to be working towards in the future. Right now, we just have image classification, but we hope to have more features as this becomes more popular. And then finally, Arun has, is there a data set limit for Dan?
So no, there is not. So we have customers who have multi-terabyte data sets. So if you're getting into the realm of multi-terabytes, you probably want to talk with us about enterprise tooling, because you're going to need some extra help managing that. But yeah, just upload as much data as you have, and we don't put any limitations on that. I
will say I've tried uploading a 10,000 image data set for training a neural network that did number recognition. So I had 1,000 images of each number from 0 through 9. The tool's kind of slow at that point. So you have a 10,000 image data set, you're getting beyond the point where you probably should start investing in building your own rig up or paying for enterprise tooling.
Yeah, so if you are hitting into that, because the issue is basically every time when you train a network for 10 epochs, for example, every epoch you're passing in your entire data set through the network. So if you do want to work with like truly large data sets, it can get kind of slow. Transfer learning speeds that up a lot, so that's nice. But if you're training from scratch, it can take a while. So if you do want to do stuff with big data, we totally support that, but let us know and we can give you access to all sorts of tools that make that easier and quicker.
All right. I think we got all the questions. Anyway, as I mentioned before, this is just the beginning. We've got image recognition working, and we're going to be building into our tool now that Arduino has backed us and wants to help grow OpenMV. With the Arduino Portenta, we really have the hardware coming out that's going to unlock the future. And so we're going to be building into OpenMV IDE all the features you need for whatever. So, we've already got the ability to open images in our IDE, which is sweet. And so the future is how can we make it have, a paintbrush tool, and you be able to actually segment and build a segmentation mask inside the IDE. And then we can store all those images in your data set and then upload those to Edge Impulse, and boom, you're now doing image segmentation and etc.
It's very cool stuff.
Ram has one more question. Is the image captured, is there any different than the image captured the same camera based on the Arduino 5 megapixel? Okay, so the OpenMV Cam H7 is a 5 megapixel image sensor. So we're downscaling it to 320 by 240 by default, just on top of the sensor. So we're not even sending a 5 megapixel image to the camera itself. I mean, from the out of the camera, we're telling the camera to output a 320 by 240 imager. And so the camera sensor itself is doing all the downscaling. And then regarding scaling and Edge Impulse, so the way OpenMV thinks about things is given the network has an input of, let's say, 96 by 96 pixels, what OpenMV does is it tries to blow up, it tries to find a square inside of your input image that is at the same aspect ratio of whatever the network is. So for example, if you have a 96 by 96 input window to the network, then any type of square resolution will be accepted. And then if you have a non-square resolution, the OpenMV will basically just center the detection window in the center of the field of view, and then apply a, and then grab that square pixel region in the center of the field of view. This corresponds to the, when you're doing the impulse design on Create Impulse, this corresponds to the resize method fit shortest axis. So that's what effectively the OpenMV Cam does for finding the, for recognizing the network. So you should always select that option to get the same performance as what the OpenMV Cam is doing. The OpenMV Cam does not squash your image because that obviously causes corruption, and does not fit longest axis because then there's a problem having to make up data for the shorter axis. And it doesn't do crop either. It does fit shortest axis. All right. Okay, I'm gonna call it at that because I just finished drinking all that water, so I gotta use the restroom. Anyway, yeah, thank you everyone for attending, and you can please, I'm gonna keep the workshop files up online indefinitely, so the link I dropped in the chat, that'll work for as long as you want. So go ahead and go online and download everything. And remember, there's videos that are already pre-recorded of all the steps too, along with the workshop script that's quite detailed. So if you want to complete this in your free time later on at your own pace, you can.
I wanted to thank you, Kwabena, for such an amazing workshop. I feel like you do workshops better than anyone. So really good job.
Yeah,
thank you so much. I'm glad it went off without a hitch.
Yeah, thank you both. That was a really good one. I like the dual OpenMV Edge Impulse workshop. And thanks everyone for attending.
Yeah, thank you all. Really excited to see what you build.
All right. Okay, take it away, Carl.
Bye, everyone.
Bye-bye.